Hello, this presentation is Available Bandwidth Adaptable Transport Protocol for Satellite Networks. Our chosen paper explores the new TCP bandwidth estimation protocol. Our presentation will start with quick introduction in TCP performance in satellite networks. After that, we will discuss our chosen network simulator and describe our protocol simulations, our results and analysis. In satellite networks, TCP has a number of performance issues, such as slow start time that leads to long propagation delays. When round-trip time increases, packet stays unacknowledged for too long time, and it leads to packet assumed lost, and it should be retransmitted again. Also, satellite links have a high error rate, and satellite links are asymmetric. So all these issues lead to frequent losses and overall TCP performance degradation. There are several possible solutions for improvement of TCP performance, such as increasing the initial congestion window size, using the explicit congestion notification capable router, or use selective acknowledgement method. Also, there are several protocols proposed for satellite networks instead of TCP, such as Satellite Transport Protocol, STP, TCP Westwood, or TCP Jersey. In our presentation, we will talk about new TCP protocol that is Available Bandwidth Adaptable Transport Protocol, which is a combination of different schemes. Our reference paper implements the ATP protocol in NS2 software, but for our project simulation, we choose the NS3 as a network simulator engine. NS3 simulator is a network simulator for research and educational purposes. It allows researchers to study internet protocols and large-scale systems. This simulator was designed to replace its earlier version NS2 that has limited realism and simplified applications. The NS3 simulator doesn't have all models that's supported by NS2, but comparing with NS2 can run more real implementation of applications and provides routing, point-to-point links, and ARP. NS3 is a fully functional simulator used to simulate IP networks, including Wi-Fi, WiMAX, LTE, and other wireless networks. There are several disadvantages of NS3. One of them that it doesn't support all models that support NS2, and for Windows systems it exists as experimental version, and it's difficult to navigate in Windows operating system. Now let's talk about Available Bandwidth Adaptable Protocol, ATP, that we want to simulate. This is a new TCP-like protocol for satellite networks. The basis for ATP is Satellite Transport Protocol, but with some modifications. Also, it adopts the bandwidth estimation algorithm of TCP Jersey protocol. This protocol allows to reduce the congestion window size based on threshold values, and offers the better performance than TCP for satellite networks. The main objectives of our simulation is to simulate ATP protocol and compare results with results in chosen research paper. The following steps were set up to accomplish our project goal. First of all, we want to simulate a simple TCP protocol, collect data, evaluate its performance over packet error rate. Next step, simulate TCP Jersey protocol by changing available bandwidth estimation algorithm in the TCP westward protocol. Simulate STP, and finally simulate our ATP protocol. After all simulation will be done, we want to analyze the data collected at each simulation, compare throughput versus PER performance for each scheme, and compare the received results with the reference paper output. And of course make conclusion about ATP performance in satellite links. To simulate TCP Jersey protocol, we need to use available bandwidth estimation algorithm. TCP Jersey protocol is based on TCP Westwood, but use different bandwidth estimation algorithm. This ABE algorithm in TCP Jersey can be evaluated using equation 1 and 2 on this slide. Equation 1 represents the bandwidth estimation at nth time, and equation 2 shows how to compute the optimal congestion window for TCP Jersey. Our target ATP protocol is based on STP protocol, and our next step for simulation is to simulate STP protocol and simulate main packets that this protocol have. STP uses 4 basic packet types, including sequence data, SD, poll, stat or status, and unsolicited status. SD is a data packet as itself. Poll is an ACK request on receiver side. Stat is the receiver response on poll messages, and UStat is autonomous request of retransmission. Receiver sends UStat messages to transmitter, and these messages indicate the lost packets in ordered sequence. The utilization of UStat packets allows a good estimation of the round-trip time values and reduces poll stat message exchange. Usually it's 3 poll messages per round-trip time.
And now I'll show you an example run of our simulation. So here we have just the run sim batch file, in which all you have to do is press enter. So we run TCP first, and each protocol will be run with multiple packet error rates. So we first start out with a very low packet error rate, and then we increase by a magnitude of 10 each time. And here what's showing on the screen is our receive drops, and what's being done in the background is the collection of our data. And so we write that to a CSV file, which is in Microsoft Excel, and from there we can create our data graphs based on that data that's been put into rows and columns for us by the simulation. This is something that we had to do in working around using the Windows version of NS3 instead of a Linux version, which has its graphing tools built in. So now we're running TCP Jersey at the different packet error rates. And then finally, we will run STP, which is an incomplete version of STP, but still gets results for us that we can evaluate despite the inexactness of it. And here we show a flowchart for the ATP protocol. We have the basic sending standard data and poll messages from STP in the middle. And this is just inherited right from STP. And then around it in the red blocks are the additional blocks, function blocks, for ATP. Starting on the top left, we have our congestion avoidance and slow start threshold management. And this is the same as over on the right in the red box. And this comes from reception of a status or unsolicited status message. The only difference being when a UStat message comes in, the advance can be the sequence number, or it can be 0 if we're getting a NAC for a packet that was meant to be sent before. In the status message, we get essentially we get an ACK for a certain number of packets, and so we open the congestion window always. For the UStat messages, we don't always open the congestion window. So those two blocks are fairly similar after we take into account the difference between status and unsolicited status message. These two blocks were put into code for the ATP simulation. The middle red block is the bandwidth estimation, and this is borrowed from TCP Jersey. This code was added for the ATP simulation as well. Basically, whenever we receive a packet, we recalculate our bandwidth, and this is the essential part for ATP, in that we are adapting to our bandwidth as we re-estimate every time based on return trip time and retransmit recovery. Now our simulation, on the right we have a basic flowchart or frame transmit scheduling of STP, which is a certain number of packets are sent, and then a poll message is sent, and the receiver will respond with a status message. And the RTT is so much so that these messages can be sent without an ACK. And this is important for our satellite link due to the large return trip time. Now the purpose here is to simulate our ATP protocol, which is combining the STP protocol and the TCP Jersey protocol. And we have the 4 basic functions of ATP, which is bulk data transfer, congestion detection, and then stat and ustat reception. Our results, starting with our TCP on the left, our congestion window. Two things happen here when we're comparing it to our packet error rate, or PER. So with our congestion window, two things happen when the packet error rate increases. One is that our congestion window never climbs as high. So we see in the blue graph, we get our congestion window to much higher levels than in the red graph. And this is because when a packet is dropped, then the congestion window has to start at its original value. The other thing that happens is that sometimes the congestion window will grow at a much slower rate. And so we see the slope of the red line become much less so than the slope of the blue lines. And that's when multiple packets are dropped in a row and we have to go into slow start and congestion avoidance. So those two things are happening with just any regular TCP connection. And we see that from when we increase our PER, we get much poorer performance. And so in figure 2, we have a comparison of TCP and TCP Jersey. TCP Jersey is incorporating a bandwidth estimation similar to TCP Westwood, and we see that when PER values are higher, we have better performance, which is the purpose of the TCP Jersey algorithm. And finally, we have STP throughput versus PER. So in our STP simulation, we were able to see that for the lower values of PER, we have higher throughput, which obviously makes sense because you're dropping less packets and you have to retransmit less. Now our results for STP aren't exact in their numbers. The STP simulation was not exactly coded to the STP standard, STP protocol standard. And this had to do with some difficulty in the simulator and understanding the simulator. But we were able to see a few different results that made sense, in that our return trip time and packet error rate and throughput were able to stay pretty much within expectations, even though the simulation wasn't exactly correct. We weren't able then to compare STP and then ATP to our TCP and TCP Jersey as the paper did, because of the incompletion in the simulation. So, as I said, in attempting to use the framework for NS3, STP wasn't really done correctly, and our ATP simulation therefore couldn't be completed, in that ATP is the combination of STP and TCP Jersey. So TCP Jersey and TCP we saw the results of and compared those, and we saw the performance of TCP Jersey being much better than TCP. However, for STP and ATP we weren't able to compare those results. And thank you very much.